All right, good afternoon, everybody, and welcome to Data Analysis and Reporting Part 2. Last month, we did some introductory information, and today we're going to elaborate and give you some really good information. I find this stuff really interesting. If you're maybe a dork like me, maybe you like it too, but we get into a lot of reporting. Again, we're very lucky to have Steve Condry and Lawrence Sproul in OQMS, and they will be presenting the material for us, or for me, I guess. Housekeeping slide, please do keep your phones and computers on mute. If you have any questions, put them in the chat box, and Lana will be monitoring that, and we'll answer them at the end of the training. In addition, we'll have a few interactive questions during the session. You can put your answers in the chat box. Steve and Lawrence are going to ask a couple things. We appreciate if you participate, nothing too hard. And always, I'll create a training course with a linked exam. I'll probably send it out next week. The transcripts are taking over 24 hours to render from Zoom. So just plan on it early next week. It will be set up as a prerequisite course. So if you have not completed part 1, you won't get part 2 until you complete part 1. And it will have a 60-day due date from when it is launched. So the objectives for today are to understand the following 6 tools: statistical measures, box plots, frequency distribution, pie charts, Pareto charts, control charts. So to understand them, when to use them, and some common mistakes to avoid. So at this time, I'd like to pass it over to Lawrence.
Thanks, Kathy. If you remember our last month's training, we talked about a lot of things related to data. We talked about using scientific methods to gain insight on our data and our processes. We talked about analyses requiring business knowledge in addition to computer skills and data science skills. We talked about the life cycle of data. We create it, store it, use it, archive it, and destroy it. We talked about the stages of analysis. We always start with a question. We collect data to support our efforts to answer the question. We clean up the data so that it's useful for our analysis. We then analyze it and interpret the results that we present to someone. And hopefully we do a good job when it produces more questions to answer. We talked about many software applications and tools available. We're going to go into more detail on some specific tools today. Just be careful how you choose what you're going to use to analyze your data, because the tools that you have may limit what you're able to do with the data. We also talked about the 4 types of analysis, which are descriptive, predictive, diagnostic, and descriptive. Today, we're going to focus primarily on descriptive, and we'll get a little bit into predictive. Some key things to pay attention to when you're doing a data analysis or reporting the results of your analysis. Really think about the audience that you're working with. Who is asking for this analysis? Who needs to know? What do they want to know? What do they want to see? How do they want to see it? Sometimes you're going to bump up against a manager that doesn't like your results. You have to be able to support it. Look for things that have a high return on investment. Look for things that are easy to get out of your analysis and have a potential for big returns. Some things that you might consider are time frames or communication processes, things that can be easily measured or calculated. Also consider the time periods that you're going to be evaluating. Think about what's gone on in the past, what changes have been made. You could do a before and after for program alignment, so check the effectiveness of that intervention. Also pay attention to trending. Trending is something that's very important. Those of you who are in and participating in a unit that gets ISO certified, it's important to be able to show your trending efforts. And for those of us who are not in an ISO certified unit, that is coming. So you should be prepared to be able to do trending as well. Another important aspect of analysis is understanding the type of data that you have. The type of data that you're working with can have very significant impact on what types of analysis and what tools you use to analyze it and what strategies you use to apply those tools. One of the most basic ways that we categorize our data is it categorical or numeric? Is it something that we can only count, or is it something that we can measure? So like examples of attribute or categorical data include things like color or some quality. Is it good or bad? Is it large or small? And the other type, ordinal or numeric, includes things like percentages, length, width, averages, and it can be also counts. The type of data, the types shown on this slide are very simplified. There are additional ways you can categorize the data, and it may be necessary to do so in order to figure out what tool you're going to use. So just learn what you can about your data and the types of information that you have so you can do the right analyses. Also be aware that some data can be transformed from one category to another. But we're not going to go into data transformations at this point. That'll be for some future training. Just another quick review. We talked about the types of analyses. Again, today we're going to focus on the descriptive, which is typically a single sample looking backwards at what has happened. We are going to go into some diagnostic where you may have multiple samples or groups of data that allow you to look back and figure out what happened. And this does include trending. We can do trending, basic trending analysis with descriptive analyses, and more advanced trending can be done with diagnostic. Now I'll pass it to Steve for the next slide.
Thank you, Lawrence. I'm going to start by discussing the normal distribution. The normal distribution or bell curve illustrates how a particular characteristic of a population sorts itself out as the population increases. Not all distributions are the same, which we will discuss later. The important things to remember from this diagram are the mean and the standard deviation. The mean is the center line that runs through the middle of the data. The standard deviations are marked along the x-axis. Another concept to remember is the central limit theorem. No matter how a population is distributed, all averages of samples drawn from that population will obey this normal distribution. This is going to be important later when we discuss control charts. Next slide, please. So we have different types of statistic measures. First, we have measures of central tendency. And we start with the mean. This is the average that we all learned in high school, where you add up all of your data points and divide by the number of data points that you have. Then you have the median, which is the value occurring in the middle of the data set when all points are listed from least to greatest. And if you have an even number of data points, you take the mean of the middle two values. And then you have the mode, which is the most frequently occurring value in your data set. Which measure you use depends upon the nature of the data. In a perfectly normal distribution, the mean, median, and mode will all be equal. If there are outliers in your data set, the median is a more robust measure. That is, it's less likely to be influenced by outliers. The mode is useful when dealing with qualitative data. That is, again, data which is counted rather than measured. Next slide. So we've dealt with the mean, the median, and the mode, which have to do with the height of the bell curve. Now we're going to talk a bit about the width of the bell curve, which is covered by the range, the standard deviation, the variance, and the coefficient of variation. And we also have a couple of other concepts we're introducing: kurtosis, which measures the length, the relationship between the height and the width, and skew, which compares the relative length of the tails of the distribution. Now you have to think about what the most likely result is going to be when you use these. The mean is the most susceptible to outliers. The median gives you half the values that are lower and half that are higher. This requires ordinal data. And the mode is, again, the value that occurs most often. It's the tallest bar in a frequency chart or histogram or Pareto chart. The geometric mean, median, and mode all reduce the impact on outliers of the result. Now, amongst the width of the bell curve measures, the standard deviation is preferred because it uses the same units as the data. The coefficient of variation is also in the same units, but it's used a little bit differently than standard deviation. It gives you more precision as opposed to accuracy. Kurtosis measures the relationship between height and width. Kurtosis and skew are important in measuring the data relative to the mean. If most points lie away from the mean, this is an indication of a high kurtosis. For example, if you have a lot of outliers in your data, this can reflect the reliability of your predictions, even if the mean is within the specification. Likewise, a high number of outliers to one side or another of the mean indicates a skewed distribution. So here we have a question. Why do we measure central tendency? A, define the best value for the average. B, attempts to find a simplified representation of the data set. C, attempts to find the root cause of a deviation. Or D, attempts to identify trends in the data. We'll give you a couple of seconds. You can enter your answers in the chat. And we're still waiting on answers.
Nobody? Not even one person wants to guess? Oh, there we go. Here's some guesses. All right. Thank you, everybody.
Okay, the correct answer is B. It attempts to find the simplified representation of a data set. Remember, the central tendency only gives you part of the picture. So in order to get more of a representation of the data, we have to go to these other measures. Next slide, please. We were discussing skewness and kurtosis. There are two other measures of central tendency. On the left, we see examples of skewness. It's a measure of the symmetry of the distribution. A positively skewed distribution has a longer right tail, and a negatively skewed distribution has a longer left tail. Now, we look at the graphs on the right. As you can see, they have the same mean, but the data are distributed differently. Kurtosis is a measure of how much data are in the tails of the distribution relative to the center. A distribution with negative kurtosis is relatively flat. A distribution with positive kurtosis has more data heat toward the center. These measures are helpful in understanding how the data lies relative to the mean. If you have a skewed distribution, it may indicate a bias in sampling or measurement. Kurtosis may reflect the indication, may indicate the prevalence of outliers in the data. So if you have a negative kurtosis, you have a process that may have a lot of outliers and is not in control. If you have a very highly positive kurtosis, that means either your process is in very tight control or somebody is cooking their data. Remember, those of you who have had background in analytical chemistry, there's always two values each equation, 0% and 100%. This is what kurtosis represents. If you're seeing an extremely high kurtosis, then you should probably investigate what's going on with the data. Next slide. Okay, going back to our normal distribution, we're going to discuss measures of statistical spread. So we have the range, which is the complete spread of data along the x-axis, and standard deviations. Again, those are marked in red along the x-axis. Now the range is the difference between the largest and smallest values. Next slide, please. The sample variance is the sum of the squares of the differences between the mean and each data point in the set divided by n minus 1. Now, if we just took the sum of all the differences, we'd get 0. That's why we take the sum of the squares of the differences so we can see just how the data is spread out. Divide by n minus 1, that gives you your sample variance. Population variance is the same as the sample variance, except the sum is divided by n. And standard deviation is just the square root of the variance. As we were saying before, the mean is only useful if one knows where the data lie relative to the mean. And the standard deviation is the most useful measure of spread, followed by the range. Again, they both use the same units of measurement as the data. Variance on its own is used in more advanced analyses not covered in this training, but it's also used to derive the standard deviation. Again, standard deviation is the square root of the variance. The rationale behind dividing by n minus 1 for sample variance is because the mean is already represented within the sample. For the population, you don't know if the mean is exactly there or not, so you have to cover all data points. Next slide, please. Now, you don't need to worry about calculating all this stuff on your own. The modern data manipulation software has all the calculations built in. You don't need to memorize any formulas. You don't need to break out your calculator. Excel with QI macros plugin, which is available through OQMS, can generate any statistical model you're likely to need as a quality professional. Just keep in mind, though, the primary limitation for Excel for statistical analysis is 1 million rows and 1 million columns of data. You're probably not going to outrun that anytime soon, but with the larger data sets coming online in the next few years, we could start running into that. And that's an issue we'll have to address then. But even then, we do have other things available to handle it. Next slide. Now, here are some common mistakes to avoid when using statistical measures. Using the wrong measure for the job, such as using means alone to compare populations when the distribution is not normal, and or without considering the standard deviation or the skewness of the distribution. Using the population rather than the sample variance for standard deviation, again, for a very large population, this will make a big difference. And making conclusions without knowing the normality of the distribution. The process with numerous outliers may be better described with the median than the mean. And the mode is better for strictly qualitative data. So know your measures and know when they're appropriate to use. For our next section, I'm going to throw it over to Lawrence to discuss the box plot.
All right, thanks, Steve. A box plot is a great way to graphically present a summary of your data. It provides what's referred to often as a 5 data point summary of your data. And those 5 data points are based on quartiles. A quartile is like a median, except that it's, instead of dividing the number of values into 2 groups, it divides it into 4 groups. So the first quartile will be from the lowest data value up to the until you have 1/4 of the data values included. The second quartile is also called the median because it adds up the remaining, so that you have half of your data values are below and half are above. The third quartile is like the first quartile, only it starts from the top. An easy way to calculate these, if you're doing it, is to do a median, and then you have a set of data from the left and a set of data from the right. You can do a second median on those subsets, and those will equal your quartiles. These are particularly valuable because you can see many things about the data. The relative length of each part of this box plot can give you indications about skew and kurtosis, in addition to their actual values for the median and the quartiles. The box area is often called the interquartile range. It's the 2 center quartiles of your data. The minimum and maximum on this chart, they're on the left, they have quotes around them because they're not a true minimum or true maximum. They're a statistical min or a statistical max that's calculated based on your data values. And that allows you to show outliers in these charts. Another common way that these are used is to compare data. And we can see that on the next slide. This is a real data set of inspections conducted by month or per month by fiscal year. And the data is interesting. It's split. We've got 2 groups of data, and each group has 3 years. So the chart doesn't automatically, when you develop these charts in Excel, it's not very good at identifying the labels for everything that you need. And so it's important to add a legend. Like what I've done here is put these colored boxes with year numbers so you can go back and forth. You do want to be careful using color. Make sure that they have a significant contrast between each color so that people who have color vision issues are more likely to be able to see and distinguish them. And you can see that each of these boxes has differences in the relative lengths of the portions of each of them. So you have the central box has a line through the middle of it. That line is the median or second quartile. And the box that Kathy is pointing at, you can see that the upper portion of that box is larger than the lower portion. That indicates that there's a skew in the data. This chart also has X's that are drawn in the box. Those X's may or may not be on the box depending on the quality of your data, but those represent the mean, which can be useful. When the mean and the median are identical, that means you've got some pretty good data, but the longer side of the box, when you have skew, is typically going to have the mean in that side. So again, that can show you more characteristics of your data. You can also see the relative lengths of the tails. Some of the longer tail and the shorter tails also give you clues about skew. You can also see that the overall length of the box varies from group to group. Those are representations of kurtosis. The shorter box has a high kurtosis and the longer box has a low kurtosis. This chart also has one outlier indicated. That's a dot above or below one of the whiskers. You can see the line at the end of the whisker is your max in this case, or the min on the bottom, and that dot is outside of that. So we have a real data point that is much higher than we would expect. That's probably some October, some September, somebody's trying to close out all their inspections. You can compare against the groups. One thing to look at, it's interesting to see that the 2019 data has higher values than 2020 and 2021. We could probably guess that that has something to do with COVID-19 because it was early in 2020 that we shut down and reduced our number of inspections significantly. But you can't just say that this is statistical difference based on this chart. It can give you clues and tell you what to test. If there is no overlap between a pair of boxes, there's a pretty good chance that it's statistically significant. It probably is. If the mean is outside of if the median does not overlap with the other boxes, then you can assume there's a possibility that it may be significant, and that whether it is or not depends on how you test the data and the results of those tests. But you'll need to do additional testing, like a z-test or an ANOVA, or one of those other statistical things to figure out how different they are. Again, you don't have to calculate the values to put in each of these. Typically, the software you use will do the calculations for you. And in some cases, the software will do an additional calculation that mark extreme outliers, which would be marked with a different symbol on these charts. All right, let's move to a question. This is a little tricky. The 5 data points summarized in a box plot are minimum, maximum, first quartile, second quartile, and third quartile. True or false? Again, we're waiting for a few people to put in some answers. All right. Yes, it is true. It's easier to say median because people have a tendency to know what that means. Second quartile can be confusing, so it's more likely that we'll say median instead of second quartile. All right, Steve, it's back to you.
Thank you, Lawrence. Now we're going to discuss frequency distribution. This is a very simple tool. We use them to compare data in multiple categories or classes. They can be used to trend data over time, and they can be used for both qualitative and quantitative data. Now remember, qualitative data is that which is counted, and quality, we refer to those as attributes, and they take on only whole number non-negative values. Quantitative is data which is calculated or variable. They can take on any value within the range of measurement. The next slide is an example of a frequency distribution that I generated a few years ago covering sample feedback reports. Now, all of this is qualitative data. We were doing strict counts of the number of sample feedback reports in several different categories. We did it by month in the fiscal year, did it by servicing laboratory, and we did it by the observations on the old sample feedback report. Those of you who have come here relatively recently, they've changed the form. So this may not look immediately familiar to you, but this is what was in use back in 2018. So next slide, please. Now, when you're building a frequency distribution, there is a risk of data loss when there are not discrete categories for the data, and you have to calculate your class boundaries. I'll get into that in the next slide, but a frequency distribution in which class boundaries must be calculated is called a histogram. Now, that last slide, we had very neat categories, very discrete categories that all the data fit into, but you may not have that with especially quantitative data. Next slide. Here's an example of data loss. To generate this histogram, I had Excel generate a list of 100 random numbers from 0 to 100. And Excel created a histogram based upon 6 subgroups, which is a good number of subgroups. But the cut points between the subgroups do not provide an accurate picture of how this data is distributed. In this last subgroup at the far right, there's a value not included in the original population. We only went to 100 and they're including 114. That doesn't even make sense. So we've lost some resolution. We also don't have a clear sense of where the mean may actually lie in this distribution. Next slide, please. Here's that same data set, but it's broken down with multiples of 10. So you have 10 subgroups, but they make a little bit more sense with regard to the data, and you get some more detail. You find out that, in fact, the distribution is bimodal, has modes at 78 and 22, that the mean isn't really all that prevalent in the population. So we end up with a potential for high kurtosis in this distribution. But knowing that the mean is bimodal, that tells you something, that you had 2 different groupings of data around 2 different points. That may be saying something about the process that you might want to investigate. So this is where you need to be careful when you're building a histogram and you have to construct your boundaries. Okay, I will go ahead and give this back over to Lawrence for pivot tables.
Thanks, Steve. Pivot tables are a very useful way to get some basic analysis on our data. And they're extremely flexible. You can get a lot of use out of these by identifying which histograms or which charts are going to be best suited for your data and what things to look at. You can easily select things, but it needs 3 things. You need something to put in the rows, something to put in the columns, and some sort of data value to put in each row and column. And they can be filtered. They're quite easy to filter to remove data that you're not interested in. You can easily change the rows, columns, and the measures. You can also do pivot charts, which are basically, they work the same way, but they have a linked chart that shows the data presented in your table in a visual way, in addition to having the table displayed. And to get to these in Excel, it's really easy. If you go into the insert menu, the first thing on the left is going to be pivot table. If you select some data, click the pivot table button, it will take you to the pivot table builder. Do be cautious though, because the next button over is recommended pivot tables. If you have a simplistic data set, it may be able to give you a good initial starting point, but typically you're going to be better off playing with the data yourself and just use the pivot table function. The next slide, we'll go into a little more detail about how these work. This pivot table was generated based on quality factor checklist data. If I remember correctly, it was regulatory notes quality factor checklist. And you're going to run into problems as you're using these that you'll have to overcome. Typically, it will be things like what is each thing represented, and so you'll have to throw in additional labels to make the data useful. Here, for example, we have in the right-hand side, you select the items to include in your chart, and typically you only want to put 3 things: something for a measure, something for a column, and something for a row. So in this case, our row labels are from the division, and our column labels are from the question number 1. Now, I'm not going to tell you what question number 1 is. I want you to think about it. What does that mean? What's the value of this data? And the people who you present this data to are going to need to know that as well. But the values represented in question 1 become these columns. We have NA, no, yes, and blank. It defaults by adding us a grand total, but those grand totals are not particularly relevant because it's a sum of across multiple quality factor checklists, and you don't really know what the number is of how many quality factor checklists were covered for each division. When you put these things in by clicking the check mark, they typically will automatically get put into either a row or a column. There are a few things that will automatically go into the values, but most of the time you're going to end up moving things around to get it in from the row or to the column or to the values. And you can easily click and drag between those 3 boxes. Do be cautious when you're working in the values area. It has to have a numerical value. So if you put in a label, like info card number, it needs a way to convert it to something, to a number that it can show. And so we used count in this, which makes sense. It gives you other options. Sometimes you might be able to do average or some other calculation on it. But for labels like info card number, you're going to want to know how many. All right. The next thing we want to talk about is pie charts. Pie charts can be good for presenting very specific types of information, but you need to be aware that they can also be very much misused. There's a respected voice in data visualization, this guy named Edward Tufte. He says pie charts are bad, and the only thing worse than one pie chart is lots of them. And the reason that is out there is that people misuse them. It's so easy to put too much data onto it, so it becomes unreadable or impossible to interpret. The things that we do, there are things that we can do to make them more useful. The primary thing is to make sure your goal of this chart is to highlight some particular feature. And that's often done by pulling one slice out so you can see it separately. There are accessibility concerns, and that's because some people have difficulty telling the difference between different shades of color. In the chart that's shown, we have one that's kind of yellowy, one that's kind of green, and one that's kind of red, and one that's kind of orange. Well, those colors happen to be difficult for some people to distinguish. So we want to do something to make sure that there's a clear delineation between them. It's also difficult for people to estimate at the area of the slice. And so we recommend that you organize them in order. Start with the largest at the top and go in order of decreasing size clockwise around, so that the largest one's going to be in the top right, and then the smallest one is going to be in the top left. Also, it's important to use labels and values so that people can have something to compare. So that rather than just relying on the actual size of the slice. Another thing to consider with a pie chart, you're dealing with typically percentages. What part of the whole is in each slice. But again, they look pretty, but the best thing you could do is highlight some particular aspect of your data. Now back to Steve.
Thank you. Now we're going to discuss the Pareto chart. Pareto charts are a specialized form of frequency distribution used to rank categories of data by prevalence to determine where and when action needs to be taken. They're used for seeking out and prioritizing potential root causes, defects, issues, or attributes. In general, according to the Pareto principle, 20% of the causes represent 80% of the nonconformances, although this is not a hard and fast rule. Next slide, please. Here's an example of a Pareto chart. It's generated in Excel and it's drawn on the same data that was used to generate the frequency distributions we saw earlier. Now you see this black arc above the data, that's called the cum line. And it indicates the cumulative percentage of the total as one progresses through each category in the chart. So we see that most of our nonconformances are indeed in these left two most columns, with a sharp drop off from the third one on. That might indicate that those where you want to take action, but next slide. Just because a defect type is more prevalent doesn't mean it's necessarily the most important issue to address. Those two first categories were minor clerical errors that didn't really have much impact on the process. We had to drill down and look at some more significant errors. A relatively rare error or nonconformance may represent a more critical outcome, such as compromise of a regulatory case, cost of correction, etc. We had some issues in that particular process where chain of custody had been violated for samples, which could have compromised the regulatory case, but certainly compromised analysis in a lot of situations. So those were the key issues we had to address. Again, knowing the process is critical in interpreting the data. Next slide. Now, going back to what Lawrence was saying about pie charts, Pareto charts are better when determining absolute percentages and as a diagnostic tool. Pie charts have their place to help in presenting visual aid to data, but most viewers have problems estimating areas in graphics. Both types of charts need to be accompanied by counts and or percentages. And again, unlike a Pareto chart, a pie chart is color dependent, which leads to 508 compliance issues for those with impaired color vision. Next slide, please. Now we're moving on to some more sophisticated tools. We're going to talk about control charts. Control charts have been in use for nearly 100 years, and they are one of the oldest quantitative tools available to quality managers, but they've endured precisely because they're a good way to portray a process in a manner that allows quick interpretation of the data. They give the voice to the process by letting the data tell how the process is changing over time, and they allow for rapid detection of deviations through trending and through plotting when a particular deviation strays too far from acceptable limits. Again, QI macros helps you choose which chart should be used. You don't have to be an expert. Next slide. Here's an example of a control chart. We'll start with the average or the center line. This is the historical average of the process. This is where the central limit theorem, which we addressed earlier in the presentation, comes into play. Each data point represents the mean for a sample from the total population of the process. So you could be sampling 5 work products at a time, taking your measurement, and that's the mean of the measurement. That's going to be a data point on your chart. Each sample is collected at regular time intervals, which are indicated on the x-axis. They calculate the center line, or the average. You would calculate the mean of all of the sample means for the time sequence in question. That's called the grand mean. The upper and lower control limits are based upon the standard deviation of the process and are calculated using the standard deviation times the constant. Again, you don't need to look up the constant. Your software can do that for you. Depending on the data, you may only have one control limit. For example, if there is an absolute minimum a process must achieve, but no maximum, only the lower control limit is necessary. More often, you'll run into a case where a value less than 1 makes no sense, such as in time frames measured in days or in attribute data where you can't have less than 0. In that case, the lower limit is going to be 0. Your software may calculate a control limit, but again, understanding the process can help you determine whether that control limit is actually meaningful. We'll see an example of this later. And here are the basic control rules. We're going to go through them as they come up in the data points, but this slide will be here for future reference. Next slide, please. And here's our first 4 rules. Rule 1 is where we have one data point beyond the limit. We see that at the far left side. We have a data point beyond the upper control limit. Now, each zone represents one standard deviation beyond the mean. So we have zone C. That's going to be within one standard deviation of the center line. Zone B is 2 standard deviations beyond the center line. And zone A is 3 standard deviations beyond the center line. Now for rule 2, this covers zone A. We have 2 out of 3 consecutive data points in zone A or beyond. Zone B, you have 4 out of 5 consecutive data points in zone B or beyond. And rule 4, 7 or more consecutive points on one side of the average in zone C or beyond. These are indications that your process is starting to run out of control and you need to take a look at it and see what's going on. Next slide. 5 and 6. If you have 7 consecutive points trending up or down, that's rule 5. And this is indicative of something running out of calibration in the lab, for example. If the calibration is starting to slip, if you have alignment starting to slip on a piece of equipment that needs to be adjusted, you'll see this trend because it'll be progressive. Number 6, well, number 6, that's a mixture. You have 8 consecutive points with no points in zone C. And that could mean changing operators, changing analysts. It could mean changing material types. It can mean a lot of different things. But the point is that the process is no longer consistent. Next slide. Rule 7 and Rule 8. Rule 7 refers to stratification and indicates when multiple processes are being included in a subgroup. So if you have work being performed on different shifts and included in the same subsample, if you've collected a sample from different lots and submitted that as a subsample, it's marked by 15 consecutive points in zone C, and that usually means that there's no consistency amongst your subsamples. Rule 8 refers to over control. This is where you have somebody is constantly intervening in the process and over adjusting as the person in charge of the process attempts to hit the mean. Those of you who've done the reading for the certification exam, you'll know about Deming's red funnel experiment. This is exactly how this looks graphically as people are trying to adjust that funnel to hit the target. Now, these rules all exist in the context of different types of control charts. The classic control chart is the X bar R chart. This is the average and range chart. These are the most common types of charts. They're used to assess samples of work product taken at predetermined intervals. The X bar S chart is used for large samples, which are greater than or equal to 10 units. And you have an individual moving range chart, which is used when it's impractical to collect more than one sample per subgroup. You have something very expensive or something that's only produced very rarely. This is when you use the individual moving range chart. These are used to measure the magnitude of a deviation from specification and utilize quantitative data about the sample or process. They're commonly associated with manufacturing, but can be used for other processes for which a quantitative measurement can be made. Next slide. Now, these charts are used for qualitative data, which is assessing the number of defects or defectives rather than the size of a deviation. Now, the number of defects refers to how many nonconformances exist within the sample. The number of defectives is how many items have defects. So we have the P chart, which is used to assess the percentage conforming or non-conforming for attribute sampling when the sample size is variable. The NP chart, which is used to plot the number of defectives when the sample size is constant. You have the C chart, used to plot the number of defects when the sample size is variable. And the U chart, which uses to plot the number of defects when the sample size is constant. So if the work product is on time frames, one would use the P or the NP chart, depending on the sample size. To assess the number of errors in a work product, the C or the U chart would be used. Next slide. And finally, we have the moving average, moving range chart, and it's used in the following situations. We have periodic collection of data, when it's necessary to collect smaller shifts of data than in other control charts, and when it may be desirable to dampen the effect of over-control. A very common application of the moving average, moving range chart is stock market report. The data is collected at periodic intervals, but very small shifts in the data can have dramatic consequences. Like if a shift in the stock price of less than 1%, that could result in a change in valuation of millions of dollars, depending on how much stock is in circulation. For our purposes, it could be a minor shift in calibration that might have a larger impact across the production line or in an analytical result. Again, QI macros can help you pick the chart you need, but you also need to understand the process that you're looking at. This cannot be emphasized enough. You will use this, and in addition to selecting the most appropriate chart for you, you can also pick which rules to highlight to automatically display the trend. You may want to look for one particular rule to take action on, and you can tell QI macros, okay, this is where we want to take action. Highlight these points that they show up. Next slide. Here's an example of a C chart. And again, this is derived from the same data set that was used for the frequency distribution in the history and the Pareto chart. It was used to track the number of sample feedback reports received over the course of the fiscal year. The center line represents the historical average. The control limits are set by the sample standard deviation and the constant. If we want to track how much the process average changes from month to month, we can use the moving average, moving range chart. In this case, we were able to detect the process deviation that was ultimately traced to a breakdown in communication between the collecting district and the service laboratory for a particular sampling assignment. That's up here at this first intervention. We're getting very close to breaking rule number 1. So we figured out what was going on with that. A new assignment had been issued. The district and the lab were reading it differently, so they just had to get on the same page and communicate that to the fields and to the analysts. And that particular observation started dropping, but we were still in danger of violating Rule 3. So we did the second intervention in conjunction with the Pareto chart that you saw. We identified some training deficits that need to be addressed. And we looked at both of the interventions. We figured out where we needed to retrain people. We implemented new training and that second intervention in June. And using these two tools in conjunction, we were able to eliminate SFRs completely by the end of the fiscal year. Now you'll note this lower control limit of 0.513, that's meaningless because we're making discrete counts. It's either going to be 0 or 1 at that level. You're not going to have 0.513 of a sample feedback report. Now, a control chart is like a run chart and that presents data over time. The target is 0 with only the upper control limit. It does add control limits to help identify when a process change is significant or if it should be ignored. It helps to determine what is an acceptable level of variation. In this case, the division had a target set of under 2% of all samples collected having a sample feedback report, which allows for some level of natural or common cause variation. People are going to make mistakes. Not all of them are serious enough to take action on. 2% was deemed acceptable by management. In this case, the corrective actions were very effective. Now we have a warning about control charts. Next slide, please. In order to use a control chart to control a process, you must determine if the process is operating in a state of statistical control to begin with. We have the process capability test, the CP and the CPK test. These are covered in the CMQ-OE certification. They're used to determine whether a process is operating in a state of control. They are beyond the scope of this training, but they are covered in—
Hi, Steve. Can you please slow down a little bit? Thank you.
Sorry.
I'm trying.
They are covered in the CMQ-OE body of knowledge. Before generating a control chart, these tests, which are mathematically very simple, are helpful in determining whether a control chart would actually provide meaningful data about the process. Even if the process is not in control, however, the control chart can be used as a diagnostic aid to determine the nature of the process deviations observed. So it gives you a good clue as to where to start looking. Even if you're not sure the process is in control, you know where to start looking to find out what to do about it. Now here's a question for y'all. Which of these charts show both kurtosis and skew? Give you folks a minute to enter your answers in the chat. Okay, seeing lots of answers of E, and that is in fact the correct answer. Both A and C, the frequency distribution and the box plot show kurtosis and skew. The control chart is influenced by these, but it doesn't show them directly in the pie chart. That just gives you a graphical interpretation of the data. It will not show anything about the distribution. Now, on that note, let's discuss some graphical presentation rules. Avoid making graphs too complex. Too much data on one graph overwhelms the reader. Avoid 3D effects. These are generally unnecessary for understanding the data. Use line graphs to display trends. Use bar graphs or pie charts to make comparisons. Consider labeling data points if doing so doesn't overcomplicate the graph. And use easy to read fonts, simple color schemes, and a legend to ease in interpreting the graph. It's also important to remember that a trend can only be established in relation to a similar time period. If you only have data for a single time period, you cannot establish a trend. Next slide. Here's some mistakes to avoid. Each column, line, or point should have a legible and commonly understood descriptor. Make sure that the labels are understood by the audience. Avoid using question 1, 2, 3, etc. Instead, use 1 to 3 word descriptors in the axis, or if they're too long to fit, use a legend. Now, the next slide, we have an example of what not to do. This graph was taken from a non-FDA site as an example of how not to visually display data. How many mistakes can you find here? We'll give you all a moment to look at that. Okay, no 3D, very good. Too many colors? Well, maybe. There's more here. Okay. Give another few seconds, let people enter their answers, and I'll go ahead and pull up the answer key. Okay, good, no data points. Okay, here's our answers. We have unnecessary 3D effects. It's very hard to read because none of the data points are labeled. The graph is at an awkward angle. It's unclear what question is being answered by the graph. They don't put anything in context. And the use of the line chart rather than the bar chart for comparisons between categories. You're not trending any data, but you are making comparisons between those categories. Now, the number of categories and the colors, now that could be a matter of opinion. The number of the categories is the number of the categories. But the problem is that it's not really clear what question this chart is answering because it's completely devoid of context and the data points aren't labeled, so you don't even see what exactly the data are. Now here's another example. This one I did draw from an FDA source on a public-facing website. It does do a few things right. It gives the percentages on the pie chart, but it makes a whole bunch of other mistakes. Can you find them all? No 3D, very good. Too many pieces of pie? Okay. We have any others? Yes, the largest section, not at 12 o'clock. Very good. Colors used too similar. Very good. Give you a few more seconds. Yes, red-green color blindness. Yes, and here's our answers. Too many categories for a pie chart. A bar chart would have been easier to interpret here. The data are not presented clockwise from the largest category to smallest. Unnecessary 3D effects. The colors are not distinct enough for 508 compliance. Some colors appear to be repeated. And a legend would be helpful, especially for the large number of categories, particularly that last puzzle piece, that last pie piece that represented 6 different categories in 1%. That could have been broken down a bit better. So that wasn't a stellar application of data presentation by whoever put this together for our website. So with that, I'll go ahead and give it back to Lawrence. He'll discuss mistakes of scale.
Thanks, Steve. This is based on a real world example, and it shows what can happen when you're showing scale. Some of you may have watched a series that included this chart on the left. The chart, both of these charts show the same data, but in different ways. The scale is adjusted. On the left, it's in a logarithmic scale, and on the right, it's a linear scale. So the values are adjusted to make the line look different. There are valid reasons that you might want to do this, but there are also reasons that you may want to avoid it. It depends on what you're trying to show with the data and to show about your population. The chart on the left was used in marketing materials to make it look like there was a minimal effect over time, when in reality, the black line in the chart on the right is showing a more accurate representation of the up and down shift. So you can use scale to hide stuff, to lie, or to expose important information about your data set. Be cautious about how you choose scale. Just because something looks nice and smooth doesn't mean that it really is. Be honest and be truthful, and be careful about selecting the scales of your data. Next slide. All right, we've finished our course today. We talked about a number of things, some key things to know about when you go about doing an analysis. Who is the data for? Who is who needs to make a decision based on your analyses? What type of data do you have? And really understanding the process can be significant. We talked about central tendency and a few ways to look at and measure the central tendency and the normality of your data, including things like skew, kurtosis, and a variety of statistical measures like mean, median, and mode. We talked about frequency distributions like pie charts, histograms, and Pareto charts, and some of the functions of each. And it's important to remember that how you group the data can be significant. It can either, a good grouping can expose valuable information, and a bad grouping can hide it. We talked a little about making pivot tables and how they are useful for exploring data by selecting and changing between rows, columns, and data values, so that you can have a quick way to identify where you could go further into your analysis. We talked a lot about control charts, the many types, and how QI macros can help you choose which one fits your data best. And it's important to remember the rules that are in place for control charts. Those rules are used to identify significant trends in your data that can inform your process. Next slide. There is a lot of things that we have not covered about data analysis, but there are great resources available for you to go out and find them. In the HHS LMS, you can search for Six Sigma control charts. You can search for statistical process control, and you can search for Excel charts and graphics. Any of those will get you quite a few courses that are relevant for how to use that particular tool. In addition, there are the ORADS courses and JRET reports courses in QMIS. And of course, we have the ASQ website, the books that we've purchased from ASQ. And one of my favorites is the ASQ monthly gifts. There's some pretty valuable analytical tools that are thrown out there for free. And they can be very useful to you. And now I'll turn it back to Kathy.
Great. Well, thank you very much, Lawrence and Steve, for a good presentation. Some is a reminder for some stuff that maybe we haven't touched on for a while. Others, I'm sure we all learned a little bit of information that we didn't know about, when to use a chart, things to avoid, things to keep in mind. When we give you this course, I will include the notes so that you have all the talking points. I didn't see any questions in the chat, but if you have any right now, you can raise your hand or just take yourself off mute. And as you go forward, if you have any questions, because this is a lot of information, a lot of it is in, some starting stuff in our book of knowledge from ASQ, but our resident experts, Steve and Lawrence, you can always reach out to them with a quick question or revisit this PowerPoint. So let me give it a couple minutes. I'll look for any hands raised. And any questions?
I see Neil was asking about the ASQ monthly gifts. They send an email out every month, but in order to get that, you have to create your own login to their website and link it to the ORA business account. There are instructions on how to do that on the SharePoint site. But yeah, they will send you that, and it's very useful. Some of the things that they send are just unbelievable.
Right, and the ASQ conference is coming up either in May or June. I know our office is going to be attending online, but there's always really good information and good online resources through the ASQ website. All right, I don't see any questions, so thank you to everybody who participated today, got involved, and a big round of applause for Steve and Lawrence. It took a lot of time to put this presentation together, but I'm very grateful that we got this information today. So thank you all and have a good rest of the day.